right, so first I would like to thank the organizers for having invited me to this workshop, and I really enjoyed those lectures by Professor Kazarian, who found a new formulation of all this. But so here I'm going to be to try to give just an overview. It's not going to be very well mathematically defined all the time. I just wanted to explain more or less what it is about, a little bit where it came from, because for many people this relation, and even for me, in fact, this relation seems a little bit miraculous. So I don't think there is really any good understanding of why it is true. I mean, we can prove it case by case, but we don't really understand why. So the deep reason. Professor Kazarian has written an equation this morning, a recursion equation in terms of Frobenius algebra. My way of writing the equation looks very different, but it's the same. I mean, it should be equivalent. I mean, it is equivalent. And also there is another way of representing that equation, which I like. It's just a picture. And the picture, more or less, means the same thing. What would be really interesting is to see whether that picture, so that picture is only a way of encoding the equation. So basically, you associate to each piece of a picture, you associate a term in the equation. It's just a graphical representation of the equation. What would be really nice, but which does not exist at the moment, is there really a geometric meaning to that picture? I mean, is there really a way of cutting surfaces into pieces which would be natural in all those, I don't know, A model, B model, or categories model, or in any other framework, for which we would have naturally such a decomposition, which would imply the topological recursion. This is unknown. So I will start by introducing what is it about. Well, the topological recursion at the moment, the state of the art, so it's not, the theory is not fully, I mean, it's not finished to be, I mean, it's a newborn theory. It's not yet completely established, but the topological recursion is mostly an algorithm, a recursive algorithm, which associates a double sequence of forms, of n forms, and also numbers, fg's, to a spectral curve. We will need to define all those things, but what is a spectral curve? In fact, again, there is not really a full agreement on that. What should a spectral curve be? But the idea is that more or less it's a kind of a plane curve or algebraic curve, not necessarily algebraic, by the way, and with some additional structure. But so it's a kind of curve, let's say. And to a curve, we associate forms and numbers by a recursion. And this recursion is completely universal. It depends on nothing. So the only thing you need to know are the initial terms. So basically, it will be the omega 01 and omega 02. And then everything is determined by recursion. And those omega gns and fg's, we shall call them the invariants of the corresponding curve. Well, what does it mean, invariants? Well, again, I don't know if there is full agreement, but OK. Why is this interesting? Well, there are two answers. One is if you take this definition, so this very abstract equation, I mean, you may wonder where it came from, but if you take this definition, it turns out that it has many, many beautiful mathematical properties. And I think this is a sufficient reason to study it, to be interested in it. It has really magical properties. For instance, just if you look at the equation here, the boundary number 1 seems to play a role very different from the other boundaries. But in fact, the result of the computation is always symmetric. And it's not obvious from the definition. I mean, in the definition, Z1 here appears only there, and it really plays a special role. But you can prove by recursion that the result is always symmetric. And only that is already magical. Another reason why those things are interesting is because they appear, this recursive structure appears in many, many applications. And it's not fully understood why, but it is so. And so all this conference is about Hurwitz numbers. I mean, this is in the title, and so in particular, it applies to Hurwitz numbers. Right. So, and among applications, so there are Hurwitz numbers, hyperbolic volumes, Gromov-Wheaton invariants. A very recent thing is not polynomials. So, for instance, the Jones polynomials. Why does it appear in that story? It's not known, but it's not even proved. It's only a conjecture. But we would like to understand it. And there are also many other problems like counting 2D or 3D partitions which are related to that. So let me introduce it really by a very simple example on an actual computation. This definition may look complicated, but let's try to see how to compute it. In fact, so this topological recursion is now taught in many places in master classes, even like in China, in Australia. And Professor Norbury in Melbourne, when he teaches it, he says that there is only one way to really understand that equation. It's try an example on compute. This is the only way to really understand what this means. So that's what he says, at least, but I agree, more or less. Okay, so the Weil-Petersson volumes, I understand that they were a little bit introduced yesterday. I don't know how much I should say about that, but just the idea is when you have, you want to compute the volume, when you have a Riemann surface of some genus with some number of boundaries, there is a unique matrix with constant negative curvature for which the boundaries are geodesics. Let's say that the length of the geodesic boundaries are given, L1, L2, Ln, all right? And you want to compute how many, in some sense, how many Riemann surfaces can have boundaries of given length. And for that, it's useful so once you have your matrix with constant negative curvature, you can cut your surface into pairs of points. The way to cut them into pairs of points is not unique. So the same surface can be cut in many ways into pairs of points, but once you have cut it into pairs of points, by pairs of points I mean whose boundaries are geodesics themselves. So, but the length of the geodesic boundaries of those pairs of points parameterize somehow all the Riemann surfaces you can obtain this way. But in fact, when you want to obtain a Riemann surface with a given boundary length, you're going to glue pairs of points together, and they should have the lengths on the boundaries have to match, but you can rotate them by an angle. And this is the meaning of that theta I. The Li's, theta I's are called the Fenchel-Nielsen coordinate of that moduli space. And the Weil-Petersson form, is just the sum over I of dLi d theta I. As I said, the decomposition into pairs of points is not unique. So for a given Riemann surface, there is not a unique definition of the Li's, theta I's, but this form is well defined, right? And out of that form, you can compute the volume of that moduli space. And so this is just a number. And in principle, it can be computed only by using hyperbolic geometry. Well, I'm not going to mention this second formula for the moment, but so it's just some numbers, so some functions of the Li's, which you want to compute. In principle, you can do that by just doing hyperbolic geometry. In fact, I prefer to consider the Laplace transforms. The Laplace transforms, so you take those volumes, multiply by e to the minus zi Li, multiply also by Li, and integrate over Li. So it's the Laplace transform. So you get some functions of variables z1 up to zn, and you would like to compute those functions. Many examples have been computed by hand. Well, V03 means you have genus 0 and 3 boundaries, so it's the pair of points itself. There is no structure on it, so the volume is 1. And if you compute Laplace transform, it's just that very simple rational fraction.
Should we multiply it by dz1, dz2, dz3?
Not for the moment. For the moment, it's a function. Later, it will be a differential form. And I will write it omega. When I multiply by the dzi, I will call it omega. Okay. Okay, for the moment, I want it to be introductory, and it's just functions, rational functions. Right. Okay. For 1, 1, 1, 1, it means one boundary on genus 1, while here you can cut it into one pair of points which you glue back together. But there is not a unique way to do that. It's a little bit more subtle how to compute the volume. But the result is that one. It's a polynomial in L1, which was not obvious from the definition. Polynomial of degree 2. You compute the Laplace transform. It's this very simple rational fraction of Z1. Okay, it's a trivial computation. Right. Other example, V04, it's a polynomial in the Li's. So you have four boundaries, so 4 lengths. It's a polynomial. The Laplace transform is again a rational fraction. Very simple. And what was found by Mariam Mirzarani in 2004 is that there is a very nice recursive relationship among those volumes. And a very nice recursion relation. Well, Mirzarani wrote the recursion relation directly in terms of the volumes. But if you Laplace transform, this is the recursion equation you get for the Laplace transforms. So this is just Laplace transform of Mirzarani's equation. And it takes this form. So you see, well, I will show you later that it corresponds to, it's a specialization of that case. But so it's just an integral involving, so you can compute some WGN in terms of some WGs, some other W's, which you have already computed before somehow. All right. So this is, but I will show you explicitly how to use this equation in 1 minute. So I mean, I don't know if it may look complicated to people who are not used to it, but I want to show that it's in fact extremely simple.
Would you give interpretation of this equation in terms of this picture?
In terms of this picture?
Yes.
Oh, it is not known. I mean, it would be very beautiful if someone would be able to interpret that in terms of that, but it is not known. I mean, the way Mirzarani proved it is really she started to study all the geodesics going from one boundary to another and used Mach chain relation. And so it's very indirect proof. The proof is very indirect, and there is no picture corresponding to that. It is not known. Right, so, excuse me? Well, all right. So let me show you how this, this equation, what does it, well, let's try to apply it when g equals 1, n equals 0 here. So let's compute W11. So it's just an example of computation. So I just rewrote the same equation. And in the right-hand side, you have only one term. So basically in this decomposition, here in the sum, I always exclude the case where one of the sides can be a disk. Okay. So in this decomposition, there is only that term. That term is absent for g equals 1 and for W11. So you have only that possibility for W11. And just means this residue with that sine function in the denominator and with W02 on the right-hand side. And remember that W02 is just defined to be as 1 over z minus z prime to the square. So it's the residue of some very simple function. Let's do it. So this is just 1 over z minus z, so it will be 1 over 4z squared. So it's 1 over 4z squared, right? Now we shall expand, so since we need to compute the residue at 0, we shall expand every function appearing here. We shall do the Taylor expansion at 0. So let's do the Taylor expansion of sine at 0 and the Taylor expansion of this very, very simple function at 0. So this is just the same as before. The sine, starts with 2 pi z minus 2 pi squared z squared over 6 and so on. We have 1 over 4 z squared. So let's put, so the pi disappears. Here we have a 2, a 4, and a z0 square. Let's put them on the front. Right, so the residue we have to compute is just that. Let's expand 1 over, well, it's just this residue. And so we have a triple pole, so it just means we need to extract the coefficient of z squared in that sum. So you can read it off. It's extremely easy. It's 1 over z0 squared plus 2 pi to the square over 6. So what you find is just that. And this matches with the known result. OK. But this matches in general. I mean, it has been proved that it's always correct. So why? Well, it's I would like to understand really. So it works. So let me show you how this Mirzahrani's recursion, so which I rewrite here again. So there is this sign 2 pi z in the denominator. How is it a special case of that one? Let me explain. So first, here, the variables we have, z0, z1, zn, and also the variable on which we integrate, z, are variables in some, well, for me, for the moment, they are variables in the complex plane, or in the Riemann sphere, the projective complex plane. Well, so they are complex numbers, but in principle, the general situation would correspond to take an arbitrary Riemann surface. All right. Then another thing is, well, since you need to integrate all the time, it's better, in fact, to use differential forms rather than functions. It's more natural. So let me turn the WGNs, which were functions, let me turn them into differential forms, symmetric differential forms. All right? And let me call that omega gn. So it's a symmetric differential form. So it just means that I take the equation, I multiply here by dz0, dz1, dzn. On the right-hand side also, I multiply by dz1, dzn. While dz0 is, I put it there because z0 appears only there, so I put the dz0 there. Well, here on the right-hand side, you see that this is nearly an omega. This is nearly the omega, but I miss the dz and the minus dz here to make an omega. Well, I have a dz here, but I don't have the minus dz. So let me put the dz and the minus dz, but since it was missing, I need to put one in the denominator now. I mean, you have minus dz and minus dz, all right. But it's just because now this makes an omega. And same thing for all the other terms. So now you can replace that by omega. So what you have is you have omegas here, omegas there, but you have a dz in the denominator. It may look strange, but remember that this is a quadratic differential. You have two dz's here in the numerator. You have one in the denominator, so the product is indeed one form. So no problem. Right now, I need to explain why we take minus z, why we take this minus dz, why we take this sign, and all that. So, and what would it would be in the general situation. So, first let me explain this 1 over z0 square minus z square. Well, just observe the following thing. 1 over z0 square minus z square, well, multiply it by 2z dz0. Then you observe that this is the integral from minus z to z of that double pole. Well, I mean, you have a simple pole at z equals z0 and a simple pole at z equals minus z0. So it's clearly an integral of that. I mean, it's triviality. And this quantity is precisely what I call omega 02. So let me replace this denominator here by this integral. So this is what I did. I replaced the denominator by this integral. And now I have a 2z dz in the denominator, and I have this sine function in the denominator also. Right? So now let me explain why we take a residue at 0. We have both factors in the denominator. Let me introduce a function which will be sine 2 pi z over 4 pi, which will be related to that, and another function which will be z square. You see that 2z dz is just the differential of x. Just 2z dz is just the differential of z square, right? And another remark is that, so the differential of z square, 2z dz, it vanishes at z equals 0. Well, this is why, I mean, we need to take the residue at a point where there is a pole, of course. But so we know that there is always going to be a pole at the zeros of dx. So the general situation would be to replace this by dx and this 0 by the zeros of dx, the places where dx vanishes. So another remark is that the minus z here is such that minus z to the square equals z to the square. So the map with z associate minus z, so let me call that map S, would be such that x, so I would call it the local involution. So it's just somehow the other solution, the other value of z, which corresponds to the same x, right? So let me replace. So here I replace the 2z dz by dx. I replace the sine, our sine 2 pi z by twice y of z minus y of minus z. Well, here y is an odd function. So y of z minus y of minus z is just twice y of z. But if we want to apply it to a more general situation, this is what we really need. And now this minus z, yeah, so sorry. Well, just another remark. If you y dx, you can call it omega 0, 1. And you see that this is y dx of z minus y dx of minus z. So you can rewrite it this way. And so the last remark is, so as I said, this map, S of z equals minus z, so which was there. Well, let's replace everywhere the minus z by this SA of z. And now we get the general topological recursion. So the general topological recursion would mean choose a function x, choose a function y, choose an omega 2, omega 0, 2, and apply the same formula now. The S would be the solution of this equation. The places where we take residues are the zeros of dx and all that. So this is the general situation. So we have turned the recursion of the Mirza-Rani's recursion into a specialization of the general topological recursion.
Question.
So,
what's the spectral curve of this? Is rational spectral curve?
sorry?
What the spectral curve of?
Well, so you had x equals z squared, and y was sine 2 pi z over 4 pi, I think. It was that. So it's not rational, but z lives on the complex plane. Well, so it depends. The underlying curve is a rational curve, but the actual function y of z is not rational. So depends what you mean by that. So the general topological recursion, I like to define it this way. So it's quite different from the definition which Professor Kazarian gave. Well, this is my way of doing it. It should be equivalent. I prefer to do it that way because there is a symmetry between x and y, which you don't see in other formulations, right? Which is not obvious at all from the definition, but it's there somehow. So this is why I prefer to write it this way, but there are many, many other ways, and I think more or less everyone who has used this recursion has written a different definition. Even myself, I think in my different papers I use different definitions. So, but well, this is one. So sigma will be, so a spectral curve for me would be the data of a certain Riemann surface, but it's not necessarily compact or connected.
But is it in all examples algebraic curve minus finitely many points?
Well, so yes, somehow what we shall really need is only germs of analytical functions at points. So you don't really need a Riemann surface, in fact. You just need some germs of analytical. So that's why it's equivalent to Professor Kazarian's formulation. What you need is just the coefficients in the Taylor expansion locally. So that's all what you need, in fact. It's the coefficient in the Taylor expansion. So I will call the branch points. So the number of branch points will be the n, which Professor Kazarian was talking about. It will be the same n somehow. So the branch point will be the zeros of dx. While in Professor Kazarian's talk, the x, well, somehow you use a local coordinate s, and the x was always x square. Well, s square over 2, in fact, in his notation. But so it's equivalent. So it's just a choice of local coordinates. Somehow s is square root of 2x. And in that case, you don't really need any more the x function. And you write the y in terms of the s function of the s coordinate. But so the involution in this case was just s to minus s. But in general, you need to compute the involution like that. And the y is more or less the equivalent of the eta of Professor Kazarian. And the omega 02 is more or less the equivalent of the t, of the bold t, or this choice of Lagrangian manifold. And it's encoded by somehow a quadratic form. Well, this omega 02 is a kind of quadratic form, so you have to make a choice. Once you have that, you can compute this recursion. So take it as a definition. You define omega gn by this definition. Right. So why is it interesting to do that? So another thing is that in this definition, what you define here, you see there is at least one. This variable is always at least, this integer is always at least 1. So this equation does never define omega g0. This equation is never defining this. So to define it, I will use exactly what was written this morning aussi. I take phi such that d phi is omega 0,1. I multiply omega g1, which was computed by the recursion. I multiply it by phi, take residues, divide by 2 minus 2g, and say, OK, this is the definition of fg, which is also the same as omega g0. It's just another name. Well, in fact, I also used to define some f0 and f1. But the definition would take, it would take a really long time to explain. It's not so complicated, but it would really take a long time to explain, so I don't want to explain it. No. Yes, this definition is only for g larger than 2.
Just in terms of notations, delta here.
You mean this? OK, I don't want to comment on that. Ask maybe Korotkin or...
This phi could be not existence, yeah. And
sorry, you only need it locally near A.
But if you have a constant, it will not change.
No, the constant does not matter because this is residueless. This is always residueless. You can prove it by recursion.
I was not asking for determination of determinant of Laplacian. Just what is a Laplacian? What coordinate?
Okay. Maybe we can discuss that later. Okay. So just a few words of how all this initially was defined. It's about matrix models. Well, initially in matrix models, what people were interested in, so in random matrices, what you have is you have a measure on a set of matrices, typically Hermitian matrices. And let's say the measure is typically dm, the Lebesgue measure of all components, exponential of trace of some polynomial of m. So this is a typical example. not the most general, but this is an example. And people in random matrices were interested in the large N behavior of all that. So exactly like Professor Kontsevich was saying, what is the large N behavior? And when you start to expand the log of a partition function, there is first an n squared term, right? Then if you go to the next order, you find that the next order is a constant. Then the next order is in n minus 2. And in fact, it goes by even powers of n. It's because of the Hermitian symmetry. If you started with an ensemble of non-Hermitian matrices like, I don't know, real symmetric, you would also find odd powers of n. But for Hermitian case, you only have even powers of n. And, well, you don't have such an expansion for every v, but let's say for a very large class of measures, you have such an expansion. And the question which existed in random matrices was how to compute the coefficients. So let's assume that you have such an expansion. How can you compute the coefficients? And also, you're not only interested in the partition function itself, but you are also interested in expectation values of the spectrum. So what is the behavior, the large N behavior of the spectrum, statistical behavior of the spectrum? And in particular, the spectrum is mostly encoded into the resolvent. So sum over I of 1 over x minus lambda I, where the lambda i's are the eigenvalues of M. So what is the statistical distribution of this quantity? You see that it will be singular exactly on the spectrum. So that's why it gives you information about the spectrum. This function. And again, you want to compute its large N expansion. Well, to leading order, you find that it behaves like n times some function. Well, it is a sum of n terms, so it's not very astonishing that it behaves like n to the power 1. I mean, 1 over n times the sum would have a limit. The next correction is in n to the minus 1. Again, it goes by only even powers of n. Then the third correction, the second correction is with n minus 3, and so on, n to the 1 minus 2g, wg1 of x. And again, the question was, how can you compute those functions, all this sequence of functions? And you can do that for higher correlation functions. So a correlation function is you take a product of resolvents. Well, take the cumulant I don't want to say what it is, but it's just a technical thing, quite easy. And this defines the endpoint correlation function. And again, start to observe how it behaves at large n. Well, at large n, it behaves like n to the 2 minus n. This is not so obvious, but that's what you observe. And then again, it goes by even powers of n. Okay, and what you want to compute now are all those coefficients, wgns. So people were interested in computing those coefficients. Well, in the literature of matrix model, there has been many methods to start trying to compute those coefficients. The first few of them, well, omega 0, 1, w01, so which is just the limit of the trace of a resolvent. It was already known by people like Wigner, Dyson, Mehta at the very beginning of random matrices. So it was known from the very beginning, and it's very easy to compute, let's say, in those examples. Then the two-point function, or the first correction to F1, to the partition function. And in some cases, people were able to go to F2, F3, and so on. It was computed more or less case by case in some simplest case. In 95, Ambjorn, Chekhov, Christian, and Malkenko produced an algorithm to, in principle, compute every coefficient. But it was an algorithm which was really model dependent. And for instance, they were able to run it only in the so-called one matrix model with polynomial potential. So it was not really written in a universal way. And the general structure was not fully understood. Then people started to be able to find general expressions for the two-point function and for the first correction F1 and so on. There are many works on that. But so in 2004, the new thing was the paper by Alexandrov, Mironov, and Morozov, and slightly later myself, where we used two different methods. But the Russians used the Virasoro constraints to find a relationship among the WGNs. I wrote the loop equations, which is very related to Virasoro constraints, but okay. But so we were able to find a recursion for those coefficients. And this recursion looked very universal. It was nearly that one. The only difference is that the denominator was not this one. It was only one term multiplied by 2 because we were studying only the hyperelliptical case where this equals minus that. And it took really a long time to understand that the good generalization was to do that. And this is what we did with Chekhov and Orantin. More than a year later, we understood that the formula which can generalize to other matrix models is when you replace this term by this difference. And really, to us, it was not obvious at that time. Okay. And then in 2007, with Orantin, we said, okay, let's study this equation, this recursion equation by itself, independently of any relationship to any matrix model, and study its properties. So, for instance, prove that it always gives something symmetric, that it has some certain invariance properties. It satisfies some equations related to what you call BCOV, and so on. So we started to redo the mathematical theory of that equation. And this is where really it started to be called the topological recursion. Right. And another surprise is that just when we finished that, physicist Marigno, well, in fact, we started to write the paper in 2006, and I was already talking a lot with Marigno, so that's why he published some things before. But Marigno realized that this recursion was also computing Gromov-Witten invariance, but at that moment, it was totally mysterious. Why? I mean, at least to me. I mean, for Marigno, it looked natural using this Chern-Simons theory and all that. But I mean, first, assuming that the Chern-Simons theory was equivalent to a matrix model, which was of a form solved by the topological recursion, was a very strong assumption, which was not at all verified at that time. And okay, well. I will not go much further on that. I just want to say something about the geometrical representation. The geometrical representation, as I said, is, well, this equation written like that, it looks complicated. But it's very easy to remember if you think of it in a graphical way. So you shall represent each of the terms here by a picture. And first, the omega gn, just represent it as a picture representing a surface of genus G with n boundaries. So it's just a picture which represents that object. Sometimes I represent it with boundaries, and sometimes with punctures. I mean, it's a matter of what you prefer. In this picture, omega 02 should be something of genus 0 with two boundaries, so it's a cylinder. Or it's also a sphere with two punctures. But very often, I shall represent it just by a straight line between x1 and x2. Okay. K, which appears here, let me represent it as, well, it's nearly a pair of points. It's more or less, the pair of points would be that. It would have three independent variables, z1, z2, z3. And so somehow, but k has only two independent variables. And it corresponds to saying that it's a pair of points, but where you have removed the legs. Well, sometimes we call it the short. I mean, I don't know. So it's like there is one boundary, but which is pinched. It's just a picture. Very often, also, it will be represented as a line with a trivalent vertex, depending on. Well,
Just mnemonic rule? Or?
yes, it's just mnemonic rule. I mean, it would be very nice to find an actual interpretation of that, but for the moment it is not known. But for the moment it's only a mnemonic rule to remember that equation. It's just a nice mnemonic rule to remember that equation. So let me show how it works in practice for computations. In practice for computation, let's say, so, well, first, there are different ways of writing the equation itself. So the recursion equation, so either you represent it with things with boundaries, and somehow it says that. It says that if you want to obtain a surface of genus G with n boundaries, let's say, you start from the first boundary, and you cut somewhere, you cut out a short, and what remains is either a surface, so is either connected, then it's of genus G minus 1, but it has one more boundary. Or the other possibility, when you remove a short, is that you get something disconnected, then you have some genus here, well, the two genus here, H and H prime, the sum is the number of holes here. And basically, the number of holes is conserved in that picture, and the number of boundaries is conserved. Another way to write it is when you represent with punctures. Well, you say that K is only that straight line with that trivalent vertex, and you glue it to two punctures. And this is the disconnected case. And this is this one is the same as this one. So these are just two ways of representing that equation, but again, it's only mnemonic rules. There is no geometry behind that for the moment. I believe there should be some geometry behind that, but it is not known. Right? So let me show you how to do, yes, and if you compute if you want to compute fg, remember that to compute fg, what you have to do is take omega g1, so something with genus G on one leg, one puncture, but on the puncture you glue this function phi, which was the antiderivative of omega 0,1. Glue means you integrate, you take the residue, and divide by 2 minus 2g, and that defines fg. Well, this is only a special case of the dilaton equation. The dilaton equation is, in general, if you have omega gn, then it is equal to omega gn plus 1, where you have glued phi to one of the legs, integrate, divided by 2 minus 2g minus n. This gives omega gn. So this is true for every n positive. And so, in fact, this case is just the case n equals 0 of that. Well, represented with boundaries, it just means that if you take the function with n plus 1 boundaries and glue a disk on one of the boundaries, divide by 2 minus 2g minus n, then you get the surface with only n boundaries. So again, it's just a mnemotechnic way, but it works. Right? So let's do some examples. So if you want to compute omega 0,3, so it's something with let's say three punctures or three boundaries. In this representation, this recursion exactly means this sum of two terms. So in fact, these are the two. There are two terms in that sum. There is no term in that part here. There are two terms. It exactly means that. So what does this picture mean? This picture just means you multiply the weight associated to each leg. So here it's the k x0z, b z bar x1. B is omega 0,2. So just take the product of those three things and integrate at the vertex. Integrate means take the residue at the branch point, at A. And you have another graph, same thing, multiply the weights of each edge and integrate at all vertices, and it gives you exactly what is written here. So it's just a mnemotechnic way, but it's very convenient. And there is a nice property is that, in fact, there is a symmetry between z and z bar. And in fact, those two quantities, so which represent a certain residue, which represent a certain integral, have the same value in the end. So you could just say it is twice that one when you compute. Let me do another one. Let me do omega 1, 1. So what this recursion means is exactly that. It's this picture. So you take a k, you glue it to a omega 0, 2. So here again, you take the product of weights associated to edges. So here this arrowed edge corresponds to k. This non-arrowed edge corresponds to omega 0, 2. Take this product, integrate, so at the branch, at the vertex, and that gives omega 1, 1. This is just a rewriting of that equation. Right. Let's do a more complicated example. Let's compute F2. F2, if you want to compute F2, you have to divide by 2 minus 2g, which is minus 1/2 in that example. Multiply by phi, so this is this red dot, it means phi. And this is omega 2, 1. So genus 2, 1 puncture. But this omega 2, 1, apply the recursion omega 2, 1 was a sum of two terms here. It was obtained like that. It was a k times some omega and some omega in that sum here, omega 1, 1 and omega 1, 1. Another term which was omega 1, 2. I mean, this is just what you obtain by this. But this one, the omega 1, 1, we have already computed this here. So let's replace this omega 1, 1 by this graph here. And for this one, again, we shall compute it by the, so this is omega 1, 2, it shall be computed by the recursion. So the omega 1, 1, I have replaced it by that graph. And the omega 1, 2, I used the recursion again. So this introduces another k. And then you have here omega 0, 3. And here you have omega 0, 2 and the omega 1, 1. Well, omega 0, 3, I replace it by this graph. There will be a factor 2. And omega 1, 1 here, I replace it by this graph. And here the omega 0, 2, it's the b. I just replace it, remember, by the straight line. So F2 is just the sum of those three graphs. Each graph means you take the product of, so to each edge, so if it is arrowed, you associate a k. If it is non-arrowed, you associate a b. Okay? You just take the product over all of them and take the residues at the vertices. But remember in which order we computed things. So it means this residues was computed first, then this one. And here in that graph, this residue is computed first, then this one, then this one. So you have to be careful about the order of residues. But you see, you can follow the order of residues. It's the inverse of the order of arrows. So it's quite easy to remember. So it's written on the graph in which order you should take residues. And it's important in which order you take residues because there are poles at coinciding points, so the order of computing residues does matter. So, so this is just the way, this is just the value of those graphs according to this equation. So for me, it's much simpler to remember those three graphs for F2 rather than all this equation. Okay, and also you have a residue to take here at the phi. Okay, but okay, this is just so those graphs are just a mnemotechnic way of writing this. But in fact, it is very useful because most of the theorems you can prove are very easy to prove graphically. So for instance, the symmetry or the BCOV-like equations are very easy to prove graphically. And also Giventhal-like formalism, it comes out very easily in graphical ways. So it's not only mnemotechnic, it's actually really useful when you want to manipulate those things.
Right. Is it the same critical points for each residue, or?
No, you have, so for each residue you have to take the sum of all critical points.
So it's actually a 4-tuple sum.
Okay, yeah. Yeah, okay. I mean, if you have n, if you have n critical points, you have yes, you have n residues here, n residues there. So here it would be you have like n to the 4 terms. I mean, this means n to the 4 terms. This picture. But you can also say that the integral means the sum of, I mean, it's only one integral, the sum of residues. I mean, it's just a matter of giving a meaning to that. So, okay, so what time should I finish?
Formally 50, I think. Let's do it later.
So, sorry, 4?
50.
Okay.
If you rest for several minutes.
No. Okay. So I just want to present very shortly some of the properties in a not very well-defined way, but just to give you an idea. Okay. Well, the first property, which is not written here, but which is extremely important, I already mentioned, is that although the recursion does not look symmetric in all its arguments, Z1 seems to play a different role. So the first boundary seems to play a different role. But in fact, you can prove by recursion that the result is always symmetric. And for instance, the graphical representation is very useful to do that. I mean, it's very easy from the graphical. Well, very easy. Well, there are a few technical steps, but I find it easy from the graphical representation. So this is not obvious at all that it's going to produce something symmetric. Even omega 0,3. Omega 0,3, remember, of Z1, Z2, Z3 was a residue of K of Z1, Z, omega 0,2 of Z, Z2, omega 0,2 of Z, Z3, well, with factor 2. Well, it does not look symmetric. But compute it, and you will find that it is always symmetric. Right? So this is not obvious, but this is, this is an important property. Otherwise, all this would not be well defined. Well, another property is the symplectic invariance. Well, to be fair, this is not really proved in general. This is only proved for special cases. But the idea is if you have this x and y here, so it means you have a curve somehow immersed into C square, CP1 to the square. You have a curve immersed into, well, either CP1 to the square or C square or whatever. But there is a very nice property that if you make, let's say, for instance, a rotation in C square, you see the notion of branch points here. The zeros of dx are the points where the tangent is vertical on that curve. And so when you make rotations, for instance, if you exchange x and y, or I mean, if you do a rotation by pi over 2, the a's will be totally different. And so all the computation here looks totally different. But when you compute the FGs, they are the same. So they are unchanged when you do that. And it is totally, the proof is totally non-trivial.
But for example, the Lambert curve, if you project it along the x-axis, it doesn't have any branch points at all.
Yeah. So what I mean by that is when both sides are well defined for this construction, then the FGs coincide. Well, there are also a few, so that's what I said. It's proved only when the curve is really algebraic. So it's really proved for algebraic. So you need both x and y to be meromorphic. And you need both x and y to have branch points. And then it is symmetric, so it is proved only in that case. So for instance, it is not proved in the case corresponding to Lambert curve or to Weil-Peterson or even for Gromov-Witten, it does not apply. For Gromov-Witten curves, it does not apply. But for Gromov-Witten, we believe that the FGs should be symmetric, but it is not proved by this proof. Okay, so in fact, we are trying to generalize the proof for non-algebraic case, but it's hard. For the moment, we have not succeeded. Another property is that the FGs you produce this way are always some modular forms, but by modular forms, I mean modular with respect to, so when this curve has some genus, it's modular with respect to the SP2G of the genus.
So it means it has some curve depends on parameters.
Yeah. Yeah.
Parameter.
But so it's so this modularity is exactly the BCOV modularity here. So I don't want to explain, but this is a property which you can prove by recursion. And in fact, for that one, the graphical method gives you an extremely easy proof that BCOV is always satisfied. So everything which satisfies this recursion will always satisfy BCOV, and this is not very difficult to prove.
And in genus 0, there's...
Well, we don't really know what modularity would mean for the genus 0 case, but okay. I mean, this is to be explored, I would say. Well, integrability. Again, this is not fully proved. This is proved only case by case for certain families of spectral curves, but it is believed that it should hold in a very, very general setting for those spectral curves. For instance, very recently, Motohiko Mulase proved that it works for Hitchin-like spectral curves, well, with rank 2 Hitchin systems. And we are working on the rank n Hitchin system case, so we can prove it. It's not published, but Mulase published it for rank 2. If you take all the series of the FGs and make this series 1 over, h bar to the 2g minus 2 FG, well, this is the tau function of some integrable system.
What are the coordinates, the independent variables?
Well,
For a moment, there is a single curve,
yes.
value. What do you mean by?
Okay, I don't want to, I mean, it will be too long to explain, but there are several natural choices of coordinates corresponding. So if you have algebraic function, meromorphic functions here, the coordinates would be the coefficient of the negative part of Laurent expansion near each pole, and that would correspond to Kp, multi-component Kp times. I mean, basically you get kind of multi-component Kp. Okay. Or for Hitchin systems, it would be the natural, I mean, the obvious choice of coordinates on the Hitchin system. Okay. Let me not go further into that direction. But so the idea is that the WG ends, well, the omega G ends will satisfy some determinantal formula, many other like precar relations, many other such relations should be satisfied, and it is not proved in general. And this is strongly related to the notion of quantum curves and all that, but there is no general proof. There is, for the moment, only case-by-case proofs. So, as I said, well, Mulase's proof is quite general, but it applies only to certain. Again, I mean, it's really a specialization of those curves. It's only a subclass of those curves. A very important property, which there I would like to say a little bit more, is about taking limits. Imagine that you have a family of spectral curves. So you have a family which depend on some time. Well, the time could be really something arbitrary. And imagine that at a certain value t equals tc, a critical time, the curve becomes degenerate. It has a cusp. Instead of having a vertical tangent, so it has no longer a tangent. Instead of having a tangent, for instance, it can have a cusp at this very special value t equals tc. When you are not at t equals tc, when you are a little bit away from t equals tc, the cusp is resolved. I mean, you have something like that. And well, so here you cannot really compute fg. But here you can compute fg as a function of this time, and you observe that it diverges as t minus tc to some power. You can compute that it diverges as t minus tc to some power, and the coefficient, so fg will diverge with t minus tc to some power, which is always proportional to 2 minus 2g. And so this t minus tc to that appropriate power times fg has a limit. And what is that limit? The miracle is that limit is also the fg of some curve, and that curve is just the blow-up of that singularity. So,
I mean, rescale it.
So yes. So, a not very rigorous way to write it is that the limit of fg of s is the FG of the limit of S. Okay, I mean, that means you need to rescale, but this is the idea. The idea is that the FGs and the omega GNs, in fact also, I did not write it, but all the omega GNs do commute with taking limits, such limits. And this is an extremely useful property. Right? And there are many, many other nice properties, but I don't have time to explain. So there are relationships with Seiberg-Witten equations. Well, the deformations, which I like to call form cycle duality, which some people call special geometry properties. Well, it's the deformation equations. I think you are going to talk about that tomorrow, probably. But so these are really nice properties. Well, you're going also to talk about the link with Giventhal formalism. Hecke algebras are also there, but I don't want to say. There is mirror symmetry. Okay, you can also extend that to non-commutative spectral curves. So you can, well, there is a notion of non-commutative spectral curve where x and y don't commute anymore, but you can apply all this formalism, and more or less it works the same way, and it enjoys more or less the same properties. I don't want to, I mean, it would go really too far. Well, let me go to examples of applications. So now let me mention some applications. So I will be very sketchy. I will not give precise definitions, for instance, about Gromov-Witten invariance or whatsoever. I will not give precise definitions. I just want to give you an idea. And most of those things are also conjectures. I mean, not everything is proved. Many of those things are not proved at all. Well, one example which emerged very recently is that topological recursion has something to do with knots, with knot theory. It's still completely, totally mysterious, and almost nothing is proved yet, but people are sure that it works. In fact, I think the first idea, the first place where it appears is a paper by Digraph and Fuji in 2009, maybe, where, well, it's about the Jones polynomial. So let me say what the Jones polynomial is. Okay, let me erase that. No, let me not say what the Jones polynomial is. People interested in knot theory have defined some invariants associated to knots. And in particular, there is one which is called the Jones polynomials, Jn. It depends on a knot, k is a knot. It depends on a variable q, and it depends on an integer n. N is usually called the color, and q is a formal parameter, and so this is a polynomial. It belongs to, I think, q of q. Maybe it's even z of q.
Yeah, maybe it's inverse power as well. Yeah.
Sorry? Yes, sorry, q and q minus 1.
It's inverse.
Sorry?
Yeah, it's integer coefficients.
Yeah, integers. So it's a certain polynomial, which is a knot invariant. And people started to be interested in how it behaves, how the log of this behaves when you send. So how does it behave when you send q to 1 and n to infinity in such a way that q log n, n log q, so let's call it u, remains finite. Well, fixed. So how does it behave? Well, and it behaves with 1 over log q times something, plus basically it will be sum of log q to some power 2g minus 1, and let's call the coefficient, log q to the k, let's call the coefficient sk of u. Well, so this will be s minus 1 of u. So there is a conjecture about s minus 1 of u, which has been there for almost 20 years, and which is not yet proved. Okay, it's called the volume conjecture. So what S minus 1 of U is, it's the volume conjecture. It goes back to Kashayev in, I don't remember when that was. Does someone know? Yeah. But the recent thing is that Digraph and Fuji claim that all the SKs here, Digraph, Fuji, and Manabe, claim that all the SKs here are basically related to the omega GNs of a topological recursion applied to a certain curve. On that curve, here, well, here I represented the figure of 8 knot. It's a very special knot. Well, I mean, not so special. I mean, it's a knot. But, I mean, it is this knot. And there is a notion of character variety associated to a knot. I don't want to enter the details, but the character variety of a knot is a curve. Well, it's an equation relating x and y, more or less like that. More or less like that. So it's an equation relating x and y. Take it as your spectral curve. Apply the topological recursion. Compute those integrals of omega gn up to u. All of them, so integrate all variables zi's. So all the zi's, integrate them up to u. Divide by n factorial, sum over g and n, such that 2g plus n minus 2 equals k minus 1. Call that sk of u. Then the conjecture is that this computes the asymptotics of John's polynomial. So, as I said, even the leading term is not proved, and is far from being proved. So, I mean, we are very far from proving the rest of the expansion. But well, what it says, we are, well, for instance, with my student, we computed, Gaëtan Borot, we computed, for this knot, we indeed computed things up to the third power of log q, and it matches. Okay, I mean, so, yeah, I mean, there are lots of numerical evidences. In fact, we can prove it for torus knots. And for torus knots, we can do not only the John's polynomials, but the Humphrey polynomials. But yes, even for that knot, it's far from being proved. For that knot, the S minus 1 has been proved by Zaghi, I think, but not the rest of the expansion, of course. So, and it's totally mysterious why it works, but it seems to work. And people are really sure that it works. I mean, most of the recent papers by Gukov are about that. So, so it's totally mysterious. Let me go to another example, which is you want to count 3D partitions. Well, 3D partitions are, or people call that also plane partitions, are you put boxes in the corner of a room. Well, but sometimes you want a room which has corners itself. Well, let's say it has a chimney or, okay? You want a room which is not necessarily a square, and you start to put boxes, and they fall from this direction. They fall from the sky, let's say, randomly, from this direction, and they go to the bottom. I mean, the room is, okay. And so it's a statistical physics problem, or it's a combinatorics problem. And the weight you put to a configuration is just the number of boxes. So yes, the weight of a configuration is just, let's say, you have a parameter q. Let's say you have just q to the power number of boxes, with q larger, q smaller than 1. So this is just how you count configurations. So you weight every configuration by that. So this is your measure on those plane partitions. And you want to compute the sum, which, well, okay, I wrote it as the number of 3D partitions of a given size, but somehow this is equivalent to say that you sum over all partitions with that power, q to the number of boxes. And you want to find the asymptotics. The asymptotics when the size of a room becomes large, so which is more or less equivalent to say the asymptotics when q goes to 1 in powers of log q. So you want to compute the asymptotics. And you can observe that the asymptotics goes by powers of the size to the 2 minus 2g, and you want to compute the coefficients fg. So what are they? Well, probably you can guess. They are related to topological recursion. At least this is the conjecture. Oh yes, sorry. When you put a lot of cubes, so here it's a configuration with very few cubes, but when you put a very large number of them, it starts to look like that. And if you observe, there are some regions where there is no cube on the walls here. And here, on the contrary, you have reached the opposite wall of the room. Can you see the colors? Yeah. And so well, here you see there is a kind of disorder, but here on those parts, there is no, since there is no cube, or here, I mean, there is no, I mean, cubes cannot move somehow here. It's frozen, it's called frozen. And there is a curve which separates the frozen region from the liquid region, and people call it the Arctic Circle. The Arctic Circle separates the liquid from the frozen region in the ocean, somehow. And the shape of that Arctic Circle has been computed. This is, for instance, a very famous paper by Kenyon, Okunkoff, and Sheffield. And for that example, they would find it is a cardioid, that curve. Well, in general, what they find is that this curve is the smallest degree algebraic curve which is tangent to all boundaries. So, and the liquid region satisfies Burger's equation, also to linear order. And so here we have a curve. We want to compute some FGs. Okay, let's make a guess. Well, in fact, it's slightly more subtle. What I think the good guess is, okay, the good guess is something slightly more subtle. Take any vertical slice of that picture and take the density of okay, plot a particle whenever there is a vertical edge. Okay. And take the density of those blue dots. And the density of those blue dots defines a spectral curve, well, which depends on which slice you choose, so which vertical slice you choose. So if you choose this vertical slice or that vertical slice or that one, you get another density. Okay? So you have a family of densities, but since they are related by Burger's equations, this means that they are all symplectically equivalent, so somehow they correspond to rotations in some sense. So in fact, they all compute the same FGs, thanks to Burger's equation. So the conjecture, which you cannot read, the conjecture is that the FGs should be the FG computed by the topological recursion applied to those densities. And somehow, well, I would say there are some cases where this is proved. It's because, in fact, this sum of our partitions is of 3D partitions is more or less what computes the Donaldson-Thomas invariance in certain Gromov-Witten theory. I mean, for certain Calabi-Yau manifolds, which is equivalent to Gromov-Witten invariance, and somehow the FGs are the Gromov-Witten invariance. And in the cases which actually correspond to an enumerative geometry problem, somehow this is proved by Okunkoff and his collaborators. But in general, for an arbitrary shape of the domain, this is not really proved.
This blue curve doesn't have any branch points again.
In fact, there is a branch point here and a branch point there.
Oh, so it is out.
Yeah, okay, it's not plotted from the computer, it's plotted by me. Okay. All right. So what I just wanted to show is if you change the vertical slice, the curve really changes, but it changes in like by a symplectomorphism, which conserves the FGs. All right. So this is just an example. Maybe I should better stop here, I think. Yeah. Well, I wanted to say a few words about Well, just another one recently. It's because the Liouville conformal field theory is becoming a very important subject nowadays because of what's called AGT conjecture, which is, I think, not really anymore a conjecture, but I mean, it depends what you call by AGT. But which says that the correlation functions of some operators in Liouville conformal field theory, I don't want to explain what this really means, are very closely related to what's called Nekrasov partition functions and all that. But so one thing is, can you compute them? In particular, can you compute them in a certain limit? Well, the Liouville conformal field theory depends on the central charge, which is usually written this way, 1 plus 6q square. And let's say, can we compute those things in the large Q limit? It's called the heavy limit. And we would like to compute this in the large Q limit. And so you want to expand that Liouville conformal field theory function into powers of Q at large Q. Again, it will go with powers of Q, well, with even powers of Q, and you would like to compute the FGs. And again, it is conjectured that the FGs here are computed by the topological recursion from a spectral curve, and the spectral curve should be y square, sorry, t is y square given by a certain expression, which is in fact what's called the tensor the stress energy tensor in Liouville conformal field theory. So the stress energy tensor gives the spectral curve, and once you know the stress energy tensor, I mean the classical limit of the stress energy tensor, you get a spectral curve, and if you apply the topological recursion to it, you should get the FGs corresponding to that large Q expansion. So this is again a conjecture, but well, we have good reasons to believe it's correct.
And what does it mean y and x in square brackets?
Non-commutative.
Yeah. Yes, non-commutative. Okay, I don't want to. So, yeah.
What does it mean?
Okay, I don't want to. Okay, I mean, there is a way to define the k in non-commutative case such that you can still apply this recursion somehow. It is something which we have done with, in particular with Chekhov and Olivier Marchal, which is here. But well, this is not finished. This is still in progress. But okay.
Yeah, but this would be kind of algebraic situation, algebraic curve, for instance.
Well, the curve is algebraic, but if you make it non-commutative, okay. Okay. Well, okay. I will just conclude. So. Initially, the topological recursion was introduced in matrix models, and indeed, it allows to find the large n expansion of matrix models by a kind of explicit algorithm. So somehow it solves the problem of computing large n expansion of matrix models. And if you abstract it from matrix models, if you apply it to an arbitrary curve, then it defines some interesting objects, which you call the invariance of that curve, and they have lots of very interesting fantastic mathematical properties, and it would be, I mean, I think they just deserve to be studied just because of that. But they have many applications, and for instance, well, the fact that they compute Gromov-Witten invariants for certain classes of Calabi-Yau, so those local toric Calabi-Yau has been proved, but...
You mean open Gromov-Witten?
Yes, open. But for those toric local Calabi-Yau, it was proved. But beyond that, nothing is really known. The fact that it applies to John's polynomials, it's a total mystery at the moment. But it's there. And so many of the interesting things to do would be to prove all those conjectures. And indeed, having a general framework to do that would be very nice. And also understanding what this picture means would be very nice. So thank you for your attention.
Is it possible in this picture to put two holes on the left, not one?
Two holes
Yeah, to have
here.
Yeah, no, to have always
Here.
only one, but one, two, and several things on
Well,
the right. Maybe it should be formal coloring, but it's still
okay. I mean,
it's like harmonic function on curve.
no, it's not. I mean, this is really the. I mean, the form of the equation really is that. Okay, I see what you mean, but so it's the other. I mean, there is something else which is called topological recursion, and where you really have one possibility with two holes on the left, but it's not that.
But you can always do it twice, right? First for the first
Yeah.
mark point and then for the second mark point.
In fact, this is for instance how we proved the XY symmetry. We do it twice, or this is also how you prove that it's symmetric in the different boundaries. You do it twice, in different orders, and you check that it matches. But I don't know.
Other questions?
Okay. Thanks.